Okay, so welcome back for the fourth lecture of the first week. So in the last lecture we discussed why is NLP hard, and we took examples of various cases of ambiguities in the language and some non-standard usage also. Okay, so today we will actually go into a real text corpus and try to study some very simple empirical laws that are very universal about language. Okay. Now before going to that, I'll try to make a simple distinction clear to you. So what are the difference between function words versus content words in language? So whenever you see a language in its vocabulary, there are various kinds of words and they can be called either function words or content words. What is the difference between those? Okay, so function words are mainly used to make the sentence grammatical. So things like various determiners, a and the and pronouns and all are function words. Content words are various nouns and verbs that convey what are the important concepts in the sentence. Okay, so content words are mainly used for determining the structure of the sentence. So now this is an example to give you an idea about what are content words and what are function words. So you see here the same sentence has been written in two different ways. In one of the cases, we have replaced the content words by some garbage words. So these mean the words that are not in the language. In the other example, we have replaced the function words by some arbitrary words that are not in the language. Okay. So can you try to find out in which sentence we have replaced the function words with something else? So you will see here in the second sentence. So we have removed the word like the and replaced it with words like glop, okay, and so on. In the first sentence, we have replaced all the nouns like angry and investigator with Winfrey Prunkenmonger. That is, it's such a garbage word. That is not the language. Now try to see the two sentences, and in which sentence you can see the structure of the sentence clearly, and in which of the sentence you can understand the topics of the sentence clearly. And you will find out that in the second sentence, you know all the topics. So it is talking about some investigator, government, and infuriated and all that. Okay, that information you cannot get from the first sentence. But in the first sentence, you can understand the structure of the sentence. The, some x, some noun, from, something, and a verb, and again a verb, all his, a noun, and a adverb. Okay, and you do not know what are these nouns and adverbs, but you know what is the structure of the sentence. There are certain fillers in the sense of various nouns and verbs. So in general, function words in a language are closed class words. What I mean by that, there are very specific grammatical categories that can be called as function words, and they are generally closed. We do not have newer and newer function words coming into a language. Okay, some examples of function words are like prepositions, pronouns, auxiliary verbs, conjunctions, grammatical articles, and various particles in the language. Okay, so now let us take a corpus and try to see what are the distribution of words that we encounter in the corpus. So here we have taken Tom Sawyer. So that was a novel written by Mark Twain, and what we are doing in this slide, we are just reporting which of the words occur with what frequency. So this is a sorted list starting from the highest frequency to some top 15-20 words, and what is the grammatical category. Okay, so the top word you see here is the, so that occurs with a frequency of 3332, and this is very common across different language corpus. Okay, so if you pick up any arbitrary language corpus, you will feel that the distribution is roughly the same. So now, can you have a look at this list and find out what is special about this list? What is the category of words that you see here? So remember, we talked about two categories, function words and content words. Can you try to find out which of the category you see here? So you will see most of the words here are function words. Okay, so like the, and, a, to, of, and you can see also by the grammatical categories, that is also written here. So one thing that we see in this distribution is that this list is dominated by the little words of English that are having very important grammatical laws for the sentence. Okay. Now, what is one exception that you see to this? Okay. So we call them function words that we said earlier: determiners, prepositions, complementizers, like the word that here. So now, what is one exception that we see in this list? So that exception is probably the word Tom. So Tom is very specific to the topic of this text. Okay, so this is about Tom Sawyer. So you see the word Tom also has a very high frequency, and this makes it to the list of top frequent words. Okay, so again, if you take an arbitrary text and try to find out some top frequent words, mostly they will be function words, also sometimes known as various stop words, plus you can find some occurrences of words that convey the topic of the text. So in this case, that is the word Tom. Now, so let us try to see something else. How many words are there in this text? What are the various technical terms by which these are indicated? So for that, we will talk about the type token distinction. So type token as such is a philosophical distinction between a concept is a type, and the particular instances of the concept. Okay, so concept is type and instances of concept are tokens. So now, what do I mean by type and token when it comes to a language? Okay, so in language, if the same word occurs multiple times, okay, so I call them the same type, same concept, but different tokens. Okay, so if I write the same word, say will, the same word twice, I say this is a single type. There is only one type, but there are two tokens. So each individual occurrence is a different token, but they are the same type. So in other sense, by type I mean some sort of unique words in my vocabulary, and token means the number of words. They are not unique. So if a word occurs 5 times, I will count it as 5 different tokens, but the same type. Now, so once we have understood what is the distinction between type and token, there is a particular concept that is called type token ratio, that is used to describe some text. Okay, so what is type token ratio? Very simply, ratio of the number of types, that is number of different unique words, to the number of running words, so all the tokens. So you find out the number of types in the text, divide by the number of tokens in the text, and you get the TTR, type token ratio. Okay, so what this ratio indicates, that tells on an average how often a new word appears in the text. Okay, so if type divided by token, that is my type token ratio, if it is high, that means in the text lot of new words keep on coming, because the number of types is very close to the number of token. But if this is small, that means the same words are getting repeated again and again in the corpus. Okay, so suppose we take two different text corpus. One is Mark Twain's Tom Sawyer, another we take complete Shakespeare's work, and we try to find out what is the TTR for each of these. So for Mark Twain, we find that there are 71,370 word tokens and 8,018 word types. So how do we compute TTR? You just find out, you just divide types by tokens. So 8,018 divided by 71,370, that will give you the TTR, that is close to 0.112. Now if you take the Shakespeare's work, you find similarly there are 84,000 plus tokens and 29,000 plus types, and TTR comes to be much lower than that of Tom Sawyer, 0.032. Okay. Now, suppose I take 4 different types of media. So 4 different types of media, like conversations, so if 2 people are conversing, academic prose, maybe scientific articles and books, news, and fiction. I take 4 different sorts of media in which language is communicated. Now, can you try to have a guess which one will have the highest TTR and which will have the lowest TTR? So let us go to the definition of TTR. So a high TTR, it will mean the tendency to use the new words. Now what about low TTR? If you have low TTR, that means tendency to use same word repeatedly. So now given that, so I have 4 different media. One are conversation, then I have academic prose, then I have news and fiction. Now which one do you think will have the tendency to repeat the same word again and again? So if you think over it, in conversation we try to repeat the same word again and again. So whatever you are conversing, I will try to take it from there and repeat it. So conversation have the tendency to use the same word repeatedly, so that means they will have the lowest TTR. Okay. On the other hand, it has been found in news you have tendency to use newer words. So news, this is the highest. Okay. So can you guess which of the remaining one will have the second lowest TTR, where the same words are being used repeatedly? And that is actually the academic prose, because academic prose is very, very formal, so there are very, very particular kind of words and verbs that we use. Okay, so that's why TTR is again found to be low in academic prose. Okay, so TTR scores the lowest value in the case of conversations and highest value in news, and academic prose has the second lowest TTR. Okay, and this also makes sense. Now one thing you must be cautious about, that TTR in itself is not a very valid measure of finding text complexity. Okay, you might say that okay, if TTR is high, text might be complex, but this is not a valid measure in itself. So why is that so? So think of the scenario, if you are using more and more text, what would happen to your TTR ratio? Okay, so suppose your text contains, so you are taking a running text, so till here you have 30,000 tokens. Now you go forward in your text and you go till 60,000 tokens. Now what would you guess? Can you say that TTR at this point will always be lower than the TTR at this point? Yes, because whatever words were there in the corpus, most of the words have already been introduced in the first half. Second half, most of the words will be again getting repeated. Okay, so the number of tokens will increase linearly with the size of text, but number of words in my vocabulary do not. Okay, so that's why if I take, say, Tom Sawyer versus Shakespeare's works, you will see the TTR is high in Tom Sawyer than Shakespeare's work, because this is having a much larger number of tokens. So in itself, it cannot be a valid measure. So we need to take into account the size of the text. So another way in which this is computed is by taking a running average. Okay, so you take a running average on some consecutive 1000 word chunks. So what do I mean by running average? Suppose I have a text that has 5000 tokens. So now you first compute TTR for the initial 1000 tokens, 1 to 1000. Okay, get a TTR for that. Now you start from 2 to 1001, again compute TTR, 3 to 1002, compute TTR, and then take an average. So you take TTR on moving window of 1000, length 1000, and then you take an average. So that is considered to be a better measure for TTR. Okay. So we say that we will talk about some empirical laws. So for that, let us try to have a look at some of the frequency distribution that we see in Tom Sawyer. Okay. So remember we said that the TTR for Tom Sawyer is roughly 0.11. So what does it indicate? It says that on an average, a word is repeated 9 times. Yes, type to token ratio is 1/9 roughly. Now what does that mean? Does that mean that each word occurs 9 times in the text, or is it something different? So what we are saying here, that words do not have a very even distribution. It does not happen that each word occurs 9 times in the text. So what is the usual kind of distribution that we see in the corpus? Okay. So on the left, in the left hand side on this slide, so you see I have 2 columns. First column gives me the word frequency, second column gives me frequency of frequency. What do I mean by frequency of frequency? How many words in this corpus have that frequency? Okay, so take the first row. That means there are 3993 words in the corpus that occur only once. They have frequency 1. And there are 1292 words in the corpus that occur twice, and so on. Similarly, there are 102 words in the corpus that occur more than 100 times. Okay, so now once you see this statistic, can you immediately see that the distribution is not very uniform? Okay, so what are the 2 different observations that we have here? So first observation that we make are most words are rare. So which are the rare words? The words that occur with frequency 1 or 2. So you see here roughly 50% of the word types. Remember in Tom Sawyer roughly 8000 word types were there. So roughly 50% of them occur only once. So they have a frequency of 1, and they are also called hapax legomena. Okay, so that is a Greek term for read only once. They occur only once in my corpus. What is the other observation that we have? 100 words account for 51% of all the tokens of all text. So you had only 102 words here that were having frequency greater than 100, but they together account for 50% of the tokens of the corpus. This is again strange. So now this particular observation gives the first empirical law that we will study, that is called JYPs Law. Okay, it's a very popular law in the case of language corpus, how the vocabularies, the distributions behave. Okay, so to see JYPs Law, what do we need to do? First, take a large corpus. Okay, now find out what are the individual word types and count the frequency of each word type. Okay, now what you need to do, you list the word types in their decreasing order of frequency. Okay, so for example, suppose in the previous case we found there are various types like the, and, Tom, and so on in the corpus. I'll find out their frequency. Suppose this occurs with 4000 frequency, this occurs with 1000, this occurs with say 2000, and this occurs with 1500, and so on. There are various words occurring with different frequencies. Now the first thing I will do, I will try to sort them in the decreasing order. So first I will have the, then I will have and, then I will have Tom, then I will have and so on, all the words in the vocabulary. So they will have their frequency. This is 4000, 1000, sorry 2000, 1500, and 1000. Now I will give them the ranks. Okay, because I have already sorted them in decreasing order, I put the rank. Suppose this is rank 1, rank 2, rank 3, rank 4, and so on. Okay, so now what does JYPs law say? So JYPs law gives me a relationship between the frequency of a word, the f in this list, and the rank of this word, okay, in this sorted list. And what is the relation that JYPs law gives? The relation is very, very easy. So relation is the frequency is inversely proportional to the rank of the word. Okay, so the inverse relationship between the frequency and the rank. So that is, I can say that if I multiply f dot r, I will get some sort of a constant. F dot r is a constant. So for our arbitrary example that we took in this case, we can even see that this holds. So 4000 into 1 is, so this is 4000, this is again 4000, this is 4500, and this is 4000. They are roughly the same. Okay. So what it means, suppose I make a list like that, and I have two words. So I have a word with has a rank of 50, another word that has a rank of 150, and I find its frequency f1, its frequency f2. So I can say that f1 is 3 times f2. So f1 is 3 times f2. Okay. So the 50th most common word should occur with 3 times the frequency of the 150th most common word. Okay. This is what JYPs law tells me. Now we can write it in also in a different manner. So we talked about frequency, we can also talk about probability. Okay. So let PR denote the probability of a word with rank r. So what is PR? PR is nothing but frequency of the word of rank r divided by the number of tokens that I see in the corpus. That's how I will compute the probability of that. So n is the total number of word occurrences. Tokens. Okay. So what does JYPs law tell? So it says frequency is inversely proportional to r. I can also write f divided by n, it's sum a by r. Okay. So what I have done, I have taken the constant k, I have written it as a times n. Okay. N is the number of tokens in my vocabulary, n is some other constant. N is fixed given a corpus, n is another constant. So now why we are doing that? Because it has been seen that in the corpus, a generally take a value close to 0.1. Okay, this is generally more fixed than the value of k. Okay. So now going back to the example of Tom Sawyer, let us take some words, their frequency and their rank, and see whether the relation that f dot r is roughly constant holds true. Okay. So what you are seeing here, so we have various words like the, and, he, there, and so on. We have written their frequencies and their ranks, and what is f dot r. So what we are seeing here, f dot r, if you start from the fourth word, say he, this remains roughly in the same range. Okay. It remains in 8000 to some 10,400 and 200. Okay. The range does not vary a lot. So that is very nice empirical evidence that JYPs law holds, and this you will see in various corpus, that f dot r remains constant for most of the words that you will see. Okay. So now, so JYPs law is one of the very, very important laws that we have just seen, but JYP has given some other laws also that are not so popular, but still we will just try to have a quick look at these. So one of the laws is relating the number of meanings a word has with its frequency. So what this law says, so the number of meanings m that a word has obeys the simple law that m is proportional to the square root of its frequency. So that is, as we have words with higher and higher frequencies, the number of different senses or the meanings in which they can be used also increases. Okay. So now if I use it with the first law, So what do we get? So the first law says that frequency is inversely proportional to the rank. This is law 1. And the second law says the meanings are directly proportional to the square root of frequency. This is law 2. If we combine these two laws together, we can get meaning are inversely proportional to the rank of a word. Okay. So that means if I put the words in the decreasing order of their rank, so starting from rank 1 to rank 2 and so on, so their number of meanings will also keep on decreasing. So these laws hold on average. Okay. What is the empirical support? So as I was saying, they hold on an average. So if we saw the words that are having rank roughly close to 10,000, so they have roughly 2.1 meanings. If they are words that are having rank roughly 5,000, they were found to have roughly 3 meanings, and the words that are having rank close to 2,000, they were having roughly 4.6 meanings. Okay, and you can do the maths and you will find out this roughly follows whatever we have seen in this law. Okay, and there is another law by JYP that tries to correlate the length of the word, that means the number of characters the word has, with the frequency of the word, and it says the frequency of the word is inversely proportional to its length. Okay, and then can you try to see that in the case of English? Some of the very long words are very rarely used, so their frequency is very small. But some of the very small words, like some simple examples like function words, they are used very often. That also makes sense because language is used for having some efficient communication. Okay, so you cannot have long words that are very common, then you will have to write a lot. Okay, so the words that are very common are generally short. Okay, so we talked about JYPs law. Now, so for doing the processing of language, what is the impact of JYPs law? So we said there is a good part and there is a bad part. So what is the good part? So in the language, we saw that, so remember there were two important observations that we made from the JYPs law. What were those? So one observation was that 50% of the vocabulary, that means the types, occur only once. So they are very rare words, and this is most words are rare words. Yes, 50% of the words occur only once. And what was the other observation? We said that roughly 100 words account for 50% of the tokens. Okay, so that is some common words are very common. They occur a lot. So words are very common. Okay, they account for roughly 50% of your text. So now, given these observations, what do you think is the good part and what is the bad part when it comes to NLP? Okay, so this is the bad part. Okay, why is it the bad part? So what it says is that for 50% of my words in the vocabulary, they occur only once, so it is not easy for me to gather some statistics, to do some meaningful analysis. So they occur only once, that's all the knowledge I have about these words. Okay, so that's why this is called the bad part. I cannot do a lot of modeling for these words. And the other part, that roughly 100 words account for 50% of the token, it's we call sometimes a good part. Why? Because for most of the analysis, you can always remove these words, and so that will reduce your total number of tokens by half. So you will have to process roughly half of the text, because half the text is simply the stop words and the function words. Okay, so that's what we meant here. The good part is that the stop words account for a large fraction of text, thus they eliminate if I eliminate the stop words, it reduces the size of my text roughly by half. And the bad part is most of the words are extremely rare, and it is very, very difficult to gather data to do some meaningful analysis with each words. Okay. So now, we will talk about one more law here. So that is the relation between the size of my vocabulary and the number of tokens in my text. Okay. So that is, how does the size of my vocabulary grow with the size of my corpus. Okay. So we talked about type token ratio. So that is one sort of analysis that we can do, but that does not give me a particular law. So what will be the rough distribution or the rough relationship between them? Okay. So we have Heaps Law that tries to give the relationship between the size of my vocabulary, that we call as V, and the number of tokens N. What this law says, that it gives a simple relationship. It says the size of my vocabulary is some constant times k, N is the number of tokens to the power beta. And the ranges are also observed in the corpus. So k has been found to be roughly in the range of 10 to 100, although this can vary. This is roughly, this has been found to be in this range, and beta is very close to the square root. So it is found in the range of 0.4 to 0.6. So what it says, so your vocabulary generally grows as per the square root of the number of tokens. So that also makes sense. Remember, we are talking about what happens if I keep on increasing my vocabulary. I'll tend to use keep on increasing my tokens, I'll tend to use the same word again and again. So number of unique tokens or unique types increase roughly to the square root of my corpus size. Okay. So what is some sort of empirical evidence for that? So here, there are 4 different corpuses that has been taken. So like Wall Street Journal, WSJ, and there are some other different news corpus. And what this plot shows, on the x-axis you have the words in my collection in millions. So how many words in my collection? So there are 10 million, 20 million, 30 million, 40 million. On the y-axis, it is showing the number of words in my vocabulary in thousands. So 20, 50,000, 100,000, 150,000, and so on. And the plot shows a relationship between the vocabulary and the number of tokens. And you see that the plot shows roughly a square root behavior. Okay. And this has been found to match with whatever Heap proposed. So this is again an empirical law that is very, very universal to the language. Okay. So that's for this lecture, and in the next lecture we will start talking about some actual task related to the pre-processing of text in the corpus. Thank you.